Okay, it looks like we have most people back. Welcome back. We've got two more talks now before the discussion session in an hour. So we're going to continue in a similar vein to the last talk with Anindita Maiti talking about a tale of symmetry and duality in neural networks. Thanks.
Thank you for the very nice introduction, and thank you for the invitation to speak at String Data. I'm very excited to be here. As my advisor Jim already mentioned, I'm going to talk about symmetry and duality in neural network ensembles. This duality, however, is different than the duality that you heard about in Jim's talk. My talk is going to be based on this paper with Jim and my collaborator Keegan Stoner in the audience. Here is a brief overview of my talk. First, a very brief introduction to neural network and Euclidean quantum field theory correspondence. Throughout the talk, everywhere that I mention quantum field theory, I actually mean Euclidean quantum field theory. Then the duality that I am going to talk about, which we call the parameter space and function space duality. Then using that duality, we came up with a technique called symmetry via duality and some of its examples. And finally, to symmetry breaking and its correlation to deep learning. Starting with a very brief introduction to neural networks. All of the people in the audience are familiar with neural networks, so I will keep it very brief. Neural networks are nothing but functions from the space of inputs to the space of outputs, defined using learnable parameters, which we collectively call theta, made of weights and biases, and discrete hyperparameters such as weight and depth. Schematically, one can think of it as an architecture made of nodes and edges with activation functions on the nodes. A natural example would be human brain, such as the picture over here. On the other hand, here is a picture of a neural network that we use in artificial intelligence and deep learning. One of the most popular examples, fully connected feed-forward one. This fully connectedness means that in each of the hidden layers, all of the nodes are connected to all the nodes on the neighboring layers. The direction from input towards output is called depth, and the direction of all the nodes across a particular hidden layer is called the weight. Hidden layers have their inputs and outputs, respectively called the pre-activation and post-activation. Here you can see the post-activation of Lth hidden layer. This is the activation function, and this is the pre-activation to Lth hidden layer. In case of fully connected feed-forward networks, each of the post-activation of hidden layers gets acted upon by a linear transformation map that you can see here. Interesting fact to note is that if you initialize a neural network in number of times, all these outputs are drawn from some distribution. So ensembles of neural network outputs at initialization can be understood or studied using statistical distribution. And as physicists, we were interested, is there any connection between Euclidean quantum field theory and the statistical distributions? And I will tell you what that connection is. To know that, first notice that in the infinite width limit, the outputs of initialized neural networks are nothing but sums over infinite number of identically and independently distributed parameters. And in statistics, we have central limit theorem, which tells us that such a sum is a draw from a multivariate Gaussian distribution. We call it a Gaussian process. Most architectures in the infinite width limit admits this Gaussian process. And not just that, if you can find the appropriate training, this Gaussian process property persists. And here are some very interesting literature if you want to look at that. We found that the output space distribution for neural networks at infinite width limit can be very well described by free scalar field theory. Additionally, close to the Gaussian process limit, for the most of the architectures, you can describe the neural network output ensembles by perturbative field theory. Again, all of the field theories are Euclidean field theory language. These were covered in our paper here. So we introduced models for the Gaussian process action and also for the non-Gaussian process action close to the infinite width limit. Here is an example of the neural network Gaussian process action. We came up with a model with two variables here. Depending on the architecture, you can have a model with 0 integrals, 0 variables, or just one variable. It is very much architecture dependent. The quadratic operator here is related to the two-point function of the neural network output ensemble by this equation when we have two variables. And depending on what the Gaussian process action is, the relation between the kernel and the quadratic operator will keep changing. For the non-Gaussian process, we introduce an effective action. Here I have the example for local interaction terms, but one can also have non-local interaction terms And we found out that there are some architectures which are better described by non-local interaction terms than others. So the non-Gaussian process effective action is something that one needs to test experimentally and see what action is the best fit. So we need some constraints to come up with the best possible model for non-Gaussian process action. And we are physicists, we notice that symmetries can be one of the best constraints that we can find to put on interaction terms. So we wanted to study the symmetries of neural network output distributions. But there was a problem. And before stating what the problem is, I'll quickly talk about what the solution to the problem is. Here is the solution to the problem. We call it parameter space and function space duality. And this is nothing but the fact that in case of neural networks, outputs and all the statistical moments can be described in two languages, in parameter space in terms of all the parameters, or in the function space in terms of the partition function. We'll take advantage of that to solve the problem. Before that, where we don't have a problem. In case of neural network Gaussian process, if we want to study the symmetries, we don't have a problem because the symmetries of the two-point functions determine the symmetries of the whole neural network output distribution. And this happens if we have a mean-free Gaussian process, because in that case, the two-point function by Wick's theorem determines all the higher order correlation functions. I have an example here. If you have parameters drawn from SOD invariant distributions, the kernel would be SOD invariant. You can notice that for a mean-free Gaussian process, which would be for this parameter choice, you will have a vanishing outpoint functions, set of vanishing outpoint functions, and you will have the higher order even point functions defined by the structure of Kronecker delta and kernels. And if you act on the output by elements of SOD group, then the transformed correlation function of the transformed outputs will still be invariant under SOD because the Kronecker deltas are invariant under SOD and so are the kernels. So this tells us that there is not a problem here. Then where is the problem? The problem is with finding symmetries for non-Gaussian processes. This happens because by choice of parameter distributions, we can ensure that the kernel or two-point function remains exact at all weight. We can do that, but the problem is with higher order correlation functions. We do not know the full action. These higher order correlation functions receive CFT corrections. So in order to find the symmetries, we need to know the full action, but we don't know that. And we take advantage of the solution that I briefly introduced in the first slide here, that you can actually study the correlation functions, their exact expressions involving integrals and parameters, parameters in the parameter space or in the parameter description. So in that way, you can learn about the symmetries of the correlation functions, even though you do not know the function space effective action. We'll take advantage of this fact. So I'm claiming here that if you act on a transformation on the output in the function space language, it will leave the functional density invariant as long as the correlation functions are invariant in the parameter space language. You can notice that here in the function space language, as long as the functional density is invariant, invariance of correlation functions is established by a simple change of variables. So we can go back to the parameter space, study the invariance of correlation functions, come back to the function space, and if the functional density is invariant, claim the invariance of the effective action. We are going to assume that the functional measure of the neural network output ensemble remains invariant. We are talking about initialized neural network ensembles, so that is going to be true. In the parameter space, we can absorb the transformation of the correlation functions into transformations of parameters, which may be just a subset of the full parameters of the neural network. If we can show that parameters distributions, PDFs, are invariant under some transformation, that transformation will leave the correlation functions invariant, and in terms, the effective action in the function space language will be invariant as well. So this is the crux of the story of how we are going to solve the problem of not knowing the symmetries in the function space language. And this is what we call symmetry via duality. In a nutshell, we are taking advantage of parameter space and function space duality, or the dual frameworks, to infer the transformation group that will leave the neural network effective action or the action at any weight invariant, all using the fact that the neural network output might be constructed as a function and parameters, or it might be some draw from a function space. And accordingly, the correlation functions have these dual descriptions. You can write them as some expression of a normalization constants, PDFs, and the output in terms of the parameters, or equivalently, you can go to the function space and describe the correlation functions in terms of the partition function, effective action, and the neural network output as draws from that function space. We are taking advantage that neural networks have two different ways of describing the same set of correlation functions, outputs, and using that to move between the two frames and find out symmetries and other constraints on the effective action when we do not know that in the function space. So this is all good in principle. But now you may ask that, is this just a conjecture that I'm coming up with, or is this something real? We found some great examples to demonstrate that, yes, this actually works for neural networks. Here are the examples. I'm a physicist, so I was interested, and my group was interested. I mean, my collaborators and advisor was interested to find out the most basic symmetries one can think of, rotations and translations. We looked into rotations in output space. Here, D is the output space dimension, and this here is the input space dimension. If we want some rotational invariance in the neural network output ensembles that keeps the output space invariant, then we need some particular choice of parameter distributions. In this case, we need the final linear layer parameters to be drawn from some SOD invariant distributions. If you have the neural network output given here by this expression where GJ is basically capturing all the complicated things that happens in the hidden layers, and this W and B are the last final linear layer parameters, and theta G are all the other parameters that goes inside all those complicated operations in the hidden layers. Then by this choice of parameter distributions, one can show that the correlation function of the transformed outputs will remain invariant just by a simple change of variables. This is the power of symmetry via duality technique. Similarly, one can show that if you are choosing the first linear layer right after the inputs to be drawn from some SOD invariant distributions, as I mentioned, this is input space dimension D, then if you act upon the inputs with some rotation group element, the the correlation function of the transformed outputs will still remain invariant by a similar mechanism, just a simple change of variables. These are great demonstrations that symmetry via duality works. But these are just rotations. Let's check the different kind of example, translation. If we act upon the input with some translation, CK can be anything. And if we define the output here, where you can see this mod operation is setting this part of the output periodic, then the correlation functions of the transformed or translated outputs will be invariant as long as you make this choice. The first linear layer weights have to be deterministic, and the bias needs to be drawn from a uniform distribution on a circle. You may ask, will such a network train at all with deterministic weights and bias with uniform distribution on a circle? We did check that. It trains. For details, you can look into our paper. So translations and rotations are not just the only kind of symmetries you can have. I'll just keep it short and just mention that you can have SUD output symmetry if you're choosing last linear layer parameters as complex. By that, I mean, you have to be specific. For the weights, you have to draw the real and imaginary parts from identical SOD invariant distributions. And similarly for the bias. For details, please check our paper. All in all, what this says is that if you're choosing the parameter distributions appropriately, you can come up with invariant neural network densities. But these are all about neural network densities at initialization. So you should ask me at this point, what about training? How does symmetry via duality work during training? And I will answer that. But before that, I will talk about a beautiful correspondence between neural networks and field theories and their symmetries. As you already grasped it from my advisor's talk, that there is a similarity between neural networks and effective Euclidean effective field theories. The inputs corresponds to space-time points, or if you're talking about quantum field theories, then the inputs indeed correspond to space-time points. The neural network output corresponds to free or interacting scalar fields. And because of these two connections, if you're talking about transformations on the inputs, that keeps the output ensemble invariant, such kind of symmetry is referred to the space-time symmetries in the field theory language. And similarly, output layer symmetries in neural network distributions correspond to internal symmetries in field theory language. And it does not stop there. Interesting fact, neural networks have many hidden layers and their internal symmetries. So you have some additional structures in neural networks that we do not see in field theory. And here, I will refer you back to my advisor Jim's beautiful talk. If you're interested, please go back and check the recording. Now coming to the training that I was talking about, how symmetry can be preserved using symmetry via duality technique during training. I'm claiming that if you want it to work, you need some constraints. The parameter distributions symmetries need to be preserved throughout training. Additionally, in the function space picture, you need to stay close to Gaussian process so that you can write down an effective action. In the parameter space, if you consider certain kind of trainings, such as I have picked up infinitesimal gradient descent here, you can notice all we would require is the invariance of this term and this term to keep the parameter distribution invariant throughout training. And this is not just a theorem that I'm claiming, this actually can happen in real life. And I'm demonstrating that by one example here. You can have output layer rotation symmetry if you consider MSE loss function and an initial parameter distribution. Please notice this is not even Gaussian distribution, just a very general SOD invariant parameter distribution. All we need is a constraint or a requirement, not just one constraint. This is one particular choice, and there can be many such choices. This particular choice of the parameter distribution and the loss function, where IP and IL are SOD invariant structures. This will give us, with infinitesimal gradient descent, an invariance of SOD symmetries throughout training in the parameter space. So in the function space, if you can write down an effective action, that is, if you stay close to the Gaussian process limit, then you can use symmetry via duality technique to find the symmetries to constrain the interaction terms that applies for the trained neural network output ensemble. This is the power of this technique. Finally, I'll end the preservation of symmetries during training with some important fact that even in the infinite width limit, when you start training, the parameters get correlated. Now, if the correlation of the parameters is small, then essentially they're getting drawn from some distribution that's close to Gaussian. And you can describe such an output ensemble using effective field theory language. And it is very much possible that symmetry properties persist in that case. I have thrown an example here. You can come up with this kind of parameter distributions during training where the parameters are correlated, but you can see SOD invariance. I'll keep it short here, but if you're more interested, you can look back to my advisor's talk for more about how symmetry breaks due to independence breaking of parameters. Finally, the last thing that I'm going to talk about is not symmetry preservation, but symmetry breaking and its correlation to deep learning. And you may ask, why does it have to be correlated? It might just be two things that happen simultaneously without any correlation. But I claim no, there is a correlation, and here's why. Look at supervised learning. What does it do? It starts with some initialized neural network distributions with zero mean, but you end up somewhere with a non-zero mean. So essentially you're flowing somewhere, breaking symmetries. In this case, you will break rotational invariance if you start with initialized neural network with zero means. So in a way, training is breaking the symmetry. It is a causation relation. But how far does this causation relation go? If you're starting with broken symmetries as initialization, will it always lead to better training? That's what we wanted to check. We ran some simple experiments and found that you need to break the symmetry intelligently. And I'll explain in 1 minute what I mean by intelligently after summarizing the experiments. For the experiments, we chose ReLU activation function with weight 50, trained on fashion MNIST with output dimension 10, and the rest of the details is in our paper. We chose all the parameters to be drawn from mean-free Gaussian distribution that would preserve the symmetry at initialization, but we wanted to break the symmetry at initialization. So for the last linear layer parameters, we chose to break symmetries in k directions out of 10. We also chose to vary this value of k for experiments. We also noticed that there is another way you can control the amount of symmetry breaking, and that's by the magnitude of the initial mean that you are turning on. So there are two independent ways of breaking the symmetry. You have initialized SOT minus k symmetry. You can vary the value of k, or you can vary the value of initial means. What we did here was we kept the value of k fixed, the number of broken directions fixed, and uniform initialized means in those broken directions, and we changed those values of initialization means. That gives us this direction. On the other hand, we decided to keep the values of the initialized means fixed and instead increased the number of broken directions. That gave us these directions. We had a ground truth close to 0, and we found that symmetries with higher networks with higher symmetries at initializations are training better. But it did not tell us whether this is an universal feature or if this is ground truth or data dependent. So for a different kind of experiment, we shifted the ground truth to some non-zero higher value. And we found that if you have some initial means that are closer to the ground truth, it trains better. In this case, we broke all the 10 directions. So there was no symmetry at initialization. And this is what I meant.
You have around 5 minutes.
Thanks, perfect. So this is what I meant by intelligently breaking the symmetry, that you have to start with some initial mean that's proportional to the ground truth. And sometimes you also need to choose the directions for breaking the symmetry intelligently. And you might ask, why go to all this trouble? What does it actually do in real life? What happens is sometimes you might have very large data set that you're trying to train on with some hidden structures and patterns. If you initialize pairs of neural networks with the directions of broken symmetry chosen orthogonally, one of the directions will perform better than the other. You can keep repeating this kind of pairs of neural nets with initialized broken symmetries in orthogonal directions. In a way, it's similar to the Gram-Schmidt decomposition that we have in linear algebra. So this way of choosing the directions of symmetry breaking at initialization will let us figure out hidden patterns and structures in very large data set that we are trying to train on. It can be potentially very interesting for machine learning community. I'll summarize. So first I talked about the duality that we used here, which is a duality between the parameter space and function space language, and how it potentially gives a way to approach field theories in parameter space. And here I will encourage you to go back and check the recording of Professor Jim Halvorson's talk on how quantum field theories are built out of neurons just using the parameter space language. Now, using the duality that I talked about, how we came up with the symmetry via duality technique, and how it lets us infer the symmetries that constrain the interaction terms in effective action at all weights, just using the invariance of parameter distributions. And then the interesting correspondence between symmetries in the input and output layers of neural networks and how it corresponds to spacetime and internal symmetries in the field theory language. An interesting fact that there are internal symmetries for multiple hidden layers in neural networks. And that's a very interesting feature that we do not see in quantum field theories. It may be very interesting for us, particle physicists, potentially. And lastly, for people who are interested in machine learning and preserving symmetries in trained networks, the trained network ensembles, you can use the symmetry via duality techniques. If you choose the PDFs, loss functions, and architectures appropriately, and train in such a way that you stay close to the Gaussian process limit throughout. And this can potentially be very interesting for people who are trying to come up with some symmetry invariant Lagrangians, such as lattice QFT. So I would wrap up here. Thank you so much. I will take questions.
Wonderful. Thank you very much for a really clear talk. Are there any questions from anybody? Tanya, yeah.
Hi, thanks for the nice talk. So the field theory you have considered, quantum field theory, is it the scalar field theory or?
Yes.
So this equivalence between this neural network and this quantum field theory, can it be also generalized for, like, say, gauge field theory, or more generic than just only scalar field theory?
Interesting question. In principle, yes, it can be found, but you have to come up with a proper kind of architecture or activation function that results in some output distribution that is corresponding to gauge fields or other kind of fields. In principle, yes, but one needs to look up into the ensembles and the architectures, which one works.
Thanks. So
maybe as a follow-on question from that, do you have a thought as to how one would be able to think about fermions in a picture like this?
Thanks, that's a great question. We found that in general, for the neural network output distributions, it is very difficult to come up with fermionic quantum fields from the usual neural network architectures that we have and the kind of operations that we have in each of the nodes. the kind of linear transformations that we have. Having said that, that does not prove that one cannot have fermionic neural networks or correspondence to fermionic distributions. It is a matter of investigation that we are looking into.
Are there any other questions? Yes, Sven.
Hey, yeah, thanks. Just a technical thing. When you were saying that non-zero mean breaks rotational invariance, I was a bit confused, because if I have a universal output, a constant output, I would still think that this has some rotational invariance.
I'm sorry, can you please explain again? I'm not sure if I understood the question.
So you had on one slide, I don't remember which slide this was, you were saying something like that if you have a non-zero mean, you're breaking rotational invariance.
I have said that in a couple of slides. One is in the initialized neural network when you have a Gaussian process limit. Is that the one that you are talking about, or it is during the training?
Well, in either case, I don't think that. So the question is, if I have an output which is has a non-zero mean, whether this breaks symmetry, yes or no? And I would say the answer to that is it depends, and it depends on if it's not just saying that it's non-zero. If it's constant, then I'm not breaking a symmetry. If I think about a perfect fluid, that doesn't break symmetry, but it has a non-zero energy density, etc., non-zero output.
I would say no if you're using the symmetry via duality technique, because we are using the fact that some parameter distributions invariance is going to make the correlation functions invariant, and we are using that to find the symmetries of the effective action. In all the examples that I talked about, if you're turning on a non-zero mean, you are having non-zero odd point functions. And if you're having non-zero odd point functions, symmetries of the kernel, at least in the Gaussian process limit, does not determine symmetries of the full distribution. So in that way, you can say that the symmetries get broken.
Okay.
So you would need some other ways to define.
You're defining that symmetry effectively as it's acting on the correlation function. Is that what you're saying?
I would say that the way we are studying the symmetries of the correlation functions is using the invariance of the PDFs, but there may be other ways of studying other kind of symmetries of correlation functions that we did not look into.
Okay. Yeah, I'll take more look on this. Thanks.
Are there any other questions? Just a very simple question. So you spoke about the symmetries of the internal layers of the neural network. Do you have any intuition as to what that might correspond to?
I'm sorry, I missed the question. Can you please repeat?
Sure. You spoke about the symmetries in the hidden layers, I guess, within the neural network. Do you have any intuition as to what that may correspond to in terms of the QFT? Thanks.
That's a great question. I have not worked on that, but I will encourage you to look into Jim Halverson's paper on that and future papers on that. And this is something, a matter of investigation that Professor Halverson is looking into right now.
Great. Sure. Thank you very much. Yeah, thank you, Anindita. That was a great talk.
Thank you so much.
Next up, we have Greg Yang.